So to begin the main part of the whole physics class, we're going to start with the token thing to start with, main first topic, and that is kinematics. So we are going to start looking at kinematics. Now, the great thing is you guys were introduced to kinematics in grade 10 science, which makes this an awful lot easier because really there aren't any major new ideas. It's mostly just about applications and practicing the actual stuff. Now, of course, kinematics, this is all about motion. It's all about the study of motion, analyzing motion and things moving. Now, there's only 4 quantities in kinematics. There is, of course, speed and velocity. Of course, something's moving, it's got to have speed or velocity. There is acceleration. There's also distance or displacement. And finally, there is time. These are the only 4 quantities in kinematics. Everything else is a modification, analysis, adjustment of these 4 main quantities, and that's it. So you got the speed, velocity, acceleration, distance, displacement, and time. Anything else other than this can be like connected to kinematics, but these are the 4 kinematic quantities. Well, 6 if you want to, double up the speed, velocity, distance, displacement, but these are the 4. So this is what we are going to be working with. Now, typically, a really, really common way to start looking at this type of stuff is looking at graphs, like motion graphs and stuff like that. And often it's really common to start with DT graphs. And there's lots of different types of DT graphs out there. One of the more simplistic ones might be just something like a straight line going across. And this, of course, would be something that is not actually moving, would be the typical thing. So something at rest because their distance isn't changing. Another simple one would look something like this. It's probably like the second easiest possible graph where, of course, something is actually moving. And, of course, this thing would have a constant speed or velocity, however you want to look at it. And then, of course, the third one that's relatively common is to have a curve of something like this. And of course, this is something that is actually accelerating, will give a curve type thing. So these are typically the common types of things that you look at in terms of DT graphs. Things not moving, moving with constant speeds, and things that are having a changing speed or are accelerating. Now, you got to be a little bit careful sometimes with graphs, whether it's a distance graph or a displacement graph. They're often totally interchangeable. But one of the key distance displacement differences is displacement graphs. If you've got a displacement graph, these are the ones that can actually go down. So for example, all 3 of these can be distance graphs, all 3 of these could be displacement graphs. But for example, what if you had something like this and the graph happened to be going something like this? It's going down. That would be a displacement graph. Distance graphs can't go down. Distance, as long as something moving, the distance you are traveling always increases. Or displacement, of course, if you guys remember from grade 10 a little bit, displacement can be measured from a reference frame of some kind. So this could be somebody, maybe this could be somebody who is maybe going home, where the actual origin represents their house. Well, if you're going home, your displacement from your house would be getting smaller, but the distance you're traveling would actually still be going up. So this could be going home, for example. This is just one example of what it could actually be. So when you're going home or going back or something, displacement can go down, but this couldn't be distance. Distance graphs, these ones always go up or stay straight, but they can't go down. Other than that, you'll see DT graph. It could be a displacement graph. It could be a distance graph. There's no real way to tell often, but if it's going down, pretty much guaranteed it's going to be a displacement graph. That's typically one of the key differences. So displacement graphs can go down, distance graphs never go down. One of the common analogies is think about the odometer on a car. The odometer on a car never goes down. As long as the car is moving, the odometer keeps on going up. because it measures the distance that's traveled in going in drive. So that's sort of like the difference between the two. Okay, so let's sort of work with this a little bit and see what else you can get. Because one of the more common things that you guys probably did is when you had your DT graphs, you know, something like this, blah, blah, blah. There's not much you can do with that one. That's kind of boring. But something like this, it's got a constant speed. So hopefully you remember, when you take the slope of this graph, this is where speed comes from. So that's because, you know, if you take two different colors here, you know, maybe that represents a green car, and this represents like a bluish type car. Which car is moving faster? Well, the blue car is moving faster because it travels a greater distance, which would be the rise, in the same amount of time, which would be the run, so rise over run. And that, of course, is slope, and that's where the idea behind speed comes from. So the slope in a DT graph, of course, gives you your speed. Now, of course, for slope, you guys are, you know, use change in y over change in x, or rise over run, but we don't have y's and x's. We don't just use arbitrary actual letters because they mean something entirely different. For us, the vertical part is distance, and the horizontal part is time. So the speed would be the change in distance over the change in time, which is just the slope of the graph. And most people don't write it like this. A lot of people will drop the little triangles, which are deltas, which of course mean change in. Most people will remember this actually as DTVs. A really common way to remember this is rearranging the expression to solve for distance. Most people remember this expression as DTV, and it's one of the most important and widely used equations in all of physics at any level, whether it's high school, university, or beyond. It doesn't matter. DTV is a good classic expression, and it comes from the slope of DT graphs. Okay, so let's start by practicing this a little bit, doing some graphical practice, and then we'll see if we can kick into other stuff as well. So I'm going to start just by drawing a little coordinate system here, a little axis. Actually, I want to make that, change the color. There we go. And let's draw another one. All right, draw a couple axes, something like this. All right, there we go. Now let's make something. We'll make a little. We're gonna make a little DT graph here, and I'm just gonna make some numbers here. And we're just doing like a rough. It's just a rough sketch of what's going on. No big deal. Something like this. All right, so I'm going to put 5s on the side and 1s on the bottom. All right, so then let's get some information going here. Let's do something like this, and we'll just use nice exact coordinates, keep things nice and simple. So I'm going to draw a line from there to there, and all the coordinates are going to be exact. Don't make this overcomplicated. And then let's draw another one. Let's go straight across, something like this. And then finally, let's draw something like that. All right, so we got 3 sections. I'm going to call it section A, call that section B, and call it section C. Okay, so what I want is, what are the speeds for the 3 sections? So what are the speeds for those 3 sections? So we got A, we got B, we got C. What are the speeds? So really what I'm asking for is the slope for the 3. That's it. So if I go to the first one, slope or the speed would be the delta D over delta T, or just distance over time, no big deal. So just find the slope of the first part. So if I look at the first part, it starts at the origin, so it makes it easy, and it goes up to 5. So the distance traveled during the first part, it went 5 meters. And how long that took? That took 2 seconds. All right, so that's it. And of course, 5 divided by 2 would be 2.5 meters per second. Okay, done. Just the slope of the graph, the first part, that's it. So then if I go to the second part is even easier. It's just going straight across. So the slope is 0. And it's staying at the same distance at 5 meters, so no big deal. So 0 meters per second for that one. That's the easy one. And for C, let's do the same type of thing. How far and how long? So how far to go? Well, it started here at 5 meters and went up to 20 meters. So it went up 15 meters. And how long did it take? Well, it went from 4 seconds to 7 seconds. So that took 3 seconds. So 15 divided by 3 would be 5 meters per second. There we go. So hopefully this is a little bit familiar or similar to some of the stuff you would have done last year when you guys were introduced to these ideas in grade 10. So now, what about if we want to look at the entire thing? What if I asked you for what's the average speed for the entire thing? Okay, what about the average speed? Well, let's see. We have 3 speeds. We've got the 2.5, we've got the 0, and we've got the 5. So what you might want to do is just add up those 3 speeds and divide by 3. But that's not correct. That's not going to work out very well. Now, the reason that doesn't work is because not all of the speeds lasted for the same amount of time. Part A, the 2.5, that lasted for 2 seconds, so did B, but the last part lasted longer. You can't just add up and divide and average out classically like this when they don't actually last for the same or for different amounts of time. The longer a speed exists, the more weight it has in the average. So instead of looking at the actual, add them up, divide by 3, we're trying to find speed. Okay, so we're trying to find the speed for the entire thing. If we're trying to find the speed for the entire thing, then let's just go back to this. DTV, distance divided by time. But instead of using the distance for one section, if I want the speed for the entire situation, I'm going to use the distance for the entire situation. We are going to use totals for this type of thing. So I don't want just any distance, I want the total distance. And the total distance, whatever the thing traveled, it started at 0, and it went all the way up to 20. So the total distance traveled was 20 meters. Well, I want to use my total time. Well, the total time went from 0 all the way up to 7 seconds. So 7 seconds. So I want to do the 20 divided by the 7. And if I divide those two out, and we've got to round off a little bit, we're right around 2.86 meters per second would be the average speed for the entire thing. Now, one slight little notation thing, you'll often see this written with a line across the top, and the line across the top means average. If you've got a whole bunch of values, a whole bunch of X values or Y value, it doesn't matter, and you put a line across the top, that means average. So it's really, really common to see DTV written like this with a line across the V, which means average V. Okay, so this is how you could find the average speed of the entire thing. And if you add up 2.5 and 0 and 5, you add them up and divide by 3, you're not going to get 2.86 meters per second. Right? You're going to get 2.5, which is wrong. Okay, so you want to do, if you're looking for the total thing, you take total distance, total time, and divide those. Okay, now what if we took the exact same thing and I asked you what are the velocities for the 3 sections? Well, this is actually really, really, really simple. The velocity for the first part is 2.5 meters per second. It's the same as this, except I'm reading it as displacement instead of distance. The velocity for the second part is 0 meters per second. There's no difference. And for C, okay, it would be 5 meters per second. Now, of course, velocities have direction. Well, the direction's actually in the answer because this is a positive 2.5. We don't write the positive, but it's positive 2.5. And this is a positive 5 because they're positive slopes. We don't have to write that, but we know that actually exists within there. And if we were actually going to then, find what is the average velocity of the entire thing, and I usually write average velocity a little bit different. I usually write average velocity as AVG for average velocity. We're going to do the similar type of thing, except instead of distance, we're going to use displacement. But the displacement's still 20, and the time is still 7, so we'll still end up with 2.86 meters per second. And there's, the little pluses inside of here because it's positive value, which is the hidden direction, so to speak, that nobody would write. It ends up being pretty much the exact same thing. So often speed and velocity end up being pretty much the exact same calculation. It doesn't have to be, and we'll look at that next, but that's generally how it works. So this sort of just comes from finding the slopes of graphs. And this is one of the reasons in grade 9 as well as in grade 10, finding slopes of graphs, there's tons of that in math class, because this is where it really starts kicking in physics and chemistry and a bunch of other stuff as well. Okay, so let's clean this up. And let's do another question, sort of show you another type of example of this type of thing. Okay, so we've got another DT graph. We'll just change things up a little bit, going up by 1s on the bottom, and then we're going up by 10s on the side. So we'll do the similar type of thing we did before. We'll just start by drawing a couple things out and get some lines on here. We'll use nice exact coordinates to make things simple. So I'm going to draw one line. I'm going to start here, and I'm going to go up to... we're going to go up to there. That's not too bad. And then we're going to draw another one. I'll go right to the top over there. I'll connect there, something like that. And then my last one, I'm actually going to go all the way down here. And something like this. Okay, so there's our 3 sections. Hopefully we can see okay exactly where the coordinates. We got this one going up to, the first part lasts till up to 2 seconds. The second part lasts up to 5 seconds. And then the last part goes all the way to 9 seconds. And let's do something similar to what we did before. I'll call that A, and I'll call that B, and I'll call that C. So let's just start very similar to what we were doing before. So what are the speeds for the 3 sections? Okay, so this is about slope again, so no big deal. So let's find the slopes. So right here, so of course your V is going to be your distance divided by your time, your slope. So go to the first part, go to part A. How far do we go? Well, we went from 20 up to 40. So it went up 20 meters. And how long that took? That took 2 seconds. So that's easy. So that's 10 meters per second. Okay. So I'll go to the second part, part B. And how far did it go? Went from 40 all the way up to 60 meters. So again, went 20 meter distance. And how long did it take? Well, this time it took 3 seconds. So we'll divide that out instead. And of course, we'll round off a little bit, but that's going to be 6.7 meters per second. And then go to the last part, C, went 60, because it starts at 60, goes all the way back down to 0. So they actually traveled 60 meters in that part, and that went from 5 to 9 seconds. That was 4 seconds. So I'll divide those two out, which gives me 15 meters per second. Now you might be looking, hey, shouldn't that 15 be negative? It's like, no, actually it's not, because speed can't be negative. Speed doesn't care which way you're going to go. That would kick in when I look at the velocities. What are the velocities? So, for example, that first one there, part A, the velocity would be 10 meters per second. No difference. Part B, 6.7 meters per second. No difference. And this is where the difference kicks in. For the last part, it would be negative 15 meters per second would be the velocity, because the distance was 60, but the displacement would be negative 60 because you're coming back. So that's where the difference would sort of kick in. Same numbers, but C gets that negative 15 for the velocity. All right, so let's do what we did before. What's the average speed for the entire thing? All right, so if I want my average speed for the entire thing, remember that's like a view with a line on top. I'm not going to use any distance in any time. I'm going to use the total distance and the total time. So how far did it go all together? Well, let's see. During the first part, starts at 20, went up to 40. So it traveled 20 in the first part. Then it traveled another 20, and then it came back 60. You could also look at your top values used for calculation. The first distance it traveled was 20. The second distance it traveled was 20. Third distance was 60. So put those together, it traveled 100 meters altogether. And how long did that take? Well, you could add your denominators if you want to, or just look at your graph. Went from 0 to 9 seconds. So that took 9 seconds. So we've just got 100 divided by 9, and that's it, which gives us an average speed of around 11.1 meters per second, which is not what you would get if you do 10 plus 6.7 plus 15, add them up, divide by 3. It's not going to be close. So that's how we could find the average speed for the entire thing. Okay, so what about the average velocity? Okay, now the average velocity isn't just going to be 11.11 because we're looking at the graph. Since the graph comes down, the displacement kicks in a little bit more. So if I look for the average velocity, so I like to write my average velocity like this, and then I often write it like this to distinguish it from that. I want my displacement. Now remember, displacement only cares about the overall result, right? So what distance did I start at? Well, I started at 20. Where did I end up? At 0. I dropped down 20 meters. Anything in between is irrelevant. It makes absolutely no difference whatsoever. So I started at 20, ended up back at 0. So I dropped 20 meters. My displacement was negative 20. All right. How long did it take? Well, that's still 9 seconds. That doesn't make any difference. So I've got the 20 and I've got the 9. So divide the 2 out, and it's negative 2.2 meters per second, which is entirely different than the 11.1. So as soon as you start changing direction, you start going back, the displacement really can change the average velocity. So you gotta be a little bit careful with that. Now, it's really kind of cool in a mathy kind of way is if I took a line and joined it from the beginning to the end, the slope of that line would be negative 2.2. Okay, it would give me that exact slope because velocity does not care about what happened. Velocity cares about what you start with and what you end with. It cares about nothing in between. The same way in the previous question, I think it looks something like this. If you had joined a line from the very beginning to the very, very end, the slope of that line would have been the average velocity and average speed, since it's always going up in that question. It makes no difference. Okay, so this is the basic graphical analysis with speeds and velocities and how to calculate total average speeds and average velocities for a situation. Remember, with the averages, you want to look at totals, total distance or total displacement, and the total time is the same for both, so it's no big deal. Okay, so this is more of a graphical type practice with this type of thing. Now, of course, we'll also do some classical type stuff with basic formulas and scenarios, but this is typically where you start with this type of thing.